to the organizers for the opportunity to participate in this wonderful workshop. I will talk about the equilibrium spatial correlations from auto-equilibrium dynamics in four-dimensional spin glasses, a work I did a while ago in collaboration with Federico Richtenseng and Giorgio Parisi. So spin glasses are random frustrated magnets where you have a magnetic impurities randomly placed in a metallic host. And the simplest model to these materials is the Edwards-Anderson model, where you have Ising spins interacting with nearest neighbors in a regular lattice with a random coupling. Interaction, it's positive, negative, and the system is frustrated. And this random interaction, random coupling, is fixed. So we say that the system has quantity disorder. So this system is a paradigmatic model, not only because it's the simplest glassy system, but also because it has many applications in different fields of science, like computational science in optimization problems. This system passes through a paramagnetic phase for high temperatures. And at low temperatures, the spins experience a cooperative random freezing that we call a spin glass phase below a certain critical transition temperature. So instead of the magnetization, the other parameter here is the overlap between two replicas of the system with the same realization of the disorder of the couplings. So two main theories explain the nature of this spin glass phase. One is the droplet theory, which is based on a Minkowski-Katanov approximation, and it's exact in one dimension, and predicts the existence of two pure states related by inversion symmetry. And the replica symmetry breaking, which is the solution to the mean field version of the model, that predicts many infinite number of pure states. So we have a non-trivial distribution of order parameters. They are organized in a ultramatic fashion. And the free energy landscape reflects this ultramaticity when you have many local minimas organized hierarchically. So we expect very slow dynamics. So this theory is it holds down to the upper critical dimension, that is 6, where the replicated field theory, based on this mean field model, predicts a Goldstone mode associated with the phase transition. So with the breaking of the continuous replica symmetry, we observe we have a soft mode, like analogous to an XY model. And this Goldstone mode we call replicon mode. So the critical phase, the spin glass phase, is a critical phase where the correlation function of the order parameter decays algebraically in the whole phase. At the critical temperature, this exponent that we call replicon exponent is the normal Ornstein-Zarnik form. And below the upper critical dimension, we expect this to be corrected by the anomalous dimension. And in the spin glass phase, above the upper critical dimension, we have this d-4 value for the replicon exponent in the zero overlap sector. And well, the randomization group is in development, and we don't know how these results extend to lower dimensions. Okay, so there is a very strong debate about the nature of the spin glass phase. I won't enter in too much detail about it. but we have a good results above an upper critical dimension, and we have very good simulations in finite dimensions. The lower critical dimension here is 2.5, most probably. And as I said before, when we do a quench from a high temperature phase to a lower to the spin glass phase, we observe a slow dynamics, where the coherence length, which is a length associated with this correlation function, grows algebraically with the time, like in critical dynamics. With Z being the dynamical critical exponent that can depend on the temperature. So in 3 dimensions, international collaboration with the help of a specially built computer for a spin machine update, let's say, have made a very good effort with unprecedented time scales in Monte Carlo simulations, and they derived a replicon exponent of 0.4 in 3 dimensions. And here the dynamical critical exponent has a 1 over T inverse temperature dependence. So the lower the temperature, the slower gets the dynamics. And our work comes to interpolate between the results, the high dimensional results and the low dimensional results. Here we will work with the Gaussian couplings, with where you know that the critical temperature is this, and we expect a slightly faster dynamics. Okay. So to deal with this very slow dynamics and obtain good results, we had to develop an intelligent scheme to the Monte Carlo simulations. We used the single instruction multiple data parallelism present in everyday processors, where you can do multiple floating point operations per cycle. So this is a capability of everyday processors. 4 40-point operations per cycle, or 8 nowadays. And so we divided the system in 4, and then we did the parallel updates of these parts. Okay, we achieved not a 20 times faster than a performance than an optimized code. It doesn't get much better than this. We naively expect 4 times the performance, but it was very good. And we simulate very many system sizes, up to 70 to linear size of 70, down to 30% of the critical temperature, with quenches. So we always simulated the dynamics, up to 10 million Monte Carlo steps, and every power of square root of 2, we saved the configuration for further analysis. We simulated 2 replicas. They begin with a random initial configuration, so they were normally relaxed in orthogonal values of the free energy, so the overlap will remain in the 0 sector until it gets very close to the equilibrium, which we'll never will achieve. So the idea of the work is to extrapolate the correlation function behavior in time to infinite time by 2 methods. So the first method is assuming an Ansatz behavior for the correlation function, or the parameter correlation function, with this stretch exponential. And we did a linear fit in space, fixing in time, fixing space, and then linear fits in space. With this, we obtain results for several system sizes and temperatures. We obtain results that the replicon exponent is almost constant in the spin glass phase. And this delta of the stretch exponential here, it's 3/2. And we obtained a good value for the dynamical critical exponent. Okay, so this is an Ansatz-dependent analysis that it's not general. So we worked with these integral estimators that have an Ansatz-independent analysis. So our analysis is based on these integrals, or this kind of averages of a power of the distance by the correlation function, and assuming this scaling law, we have these relations between the coherence length and the integral estimators. Yes, okay. We did a careful analysis of the system size, and we saw that whenever the coherence length is far away from 1/2 of the system size, 1/7 of the system size, it begins to. Yeah, I can show you. Okay, how do you? Enter. Don't open in Mac. How do you open the file? Double click. Okay. So here it is. The same graph. Yeah. Thank you. Thank you for your question. Very good question. The coherence length for various system sizes, and we see the departure from the infinite limit in this times. Okay, so if we can derive the scaling function for these dynamics. But we did this analysis not for all temperatures, because as we will see, the lower temperatures. Okay. So I don't know how to work with Mac. How do I come back to the? All right. All right. Thank you. Sorry for that. So we managed the finite size effects. We had them under control, and this is our result. We have the coherence length dependence for several decades of time. I show here only the biggest system size for the several temperatures. And in the short scales, in short time scales, we have a lattice effect. And in the long time scales, we have a departure here. Apart from the finite size effect, that is due to the ill-behaved tail of the correlation function. That's the non-self-averaging part of the correlation function. So, in order to extract so here we obtained the dynamical critical exponent in the good part of the data. But to obtain the replicon exponent, we realized that both these quantities have the same issue in the same way. So if we do a plot of the coherence length by an integral estimator, we can obtain alpha. All right. So we obtain an almost one replicon exponent in the spin glass phase, and in the critical temperature, we obtain an alpha compatible with an anomalous exponent of minus 0.223, which is an improvement of a normal finite size scaling, which goes up to 10 system size. Yeah. So no, it's all dynamics, and both of them are initialized in the same simulation. And since the dynamics, since there's no reason for them to to it's an equilibrium. Yeah, I should be clear before. It's an auto equilibrium. So all of this is auto equilibrium. We're extrapolating the data to infinite time. So that's these two graphs summarize our main results. We have obtained a dynamical critical exponent that depends on the inverse of temperature with this relation, and a replicon exponent that is almost constant in the spingless phase. We have used only this data to obtain this value. Okay, so we improved very much the estimations of the replicon exponent and the dynamical critical exponent from previous works. And as an possible outcome of this work, we can use the same technique to analyze the different overlap sectors of the spingless phase by constraining the dynamics. So we allow only spin flips in both replicas, so that they stays above a lower bound of Q. Okay. So the few theoretical predictions for the replicon exponent in the different overlap sectors are these. This is the zero overlap sector that I just showed you. This is the between the zero and the Edwards-Anderson overlap. Yeah. So we did for this very under control situation, and a preliminary analysis. This is in function of Q of the replicon exponent is instead of a discontinuous behavior from the zero sector to the finite Q sector and the Anderson parameter, we obtain an almost square Q dependence. So this is not a complete work because this is not the Edwards-Anderson parameter. We have to measure it from spatial-dissipation relation. And this it's a future improvement of the results. So thank you for your attention.